Welcome back after lunch. I think Tom put me on the program after lunch on purpose because after lunch you always have your dip, and I'm different from Tom. It's maybe easier for you my session than his sessions. I'm not sure because usually I don't go. I'm not this computer science geek who does a lot of R and things like that. I'm more like a statistician. I think maybe it's also our age or generation difference, I'm not sure. So I'll just have a traditional presentation, and I might actually even want to use the whiteboard, or I have something over here to write things down. And we have 2 hours for this block. The lecture should be like about 1 hour, and then we will do the computer practical. That was originally the idea, but actually what we will do, we'll just continue what Tom did before lunch. And I think Tom will take care of that, but I'll be here too, and then we can start interpreting things. So what are we going to talk about? Well, we're going to talk about validation and prediction error. So this is really about the accuracy. So before lunch, we really learned a lot about machine learning, how we can use machine learning, also including the spatial distances to observations in predicting, in making soil maps. So the core, or the interest of this afternoon is this session, this 2 hour block. How accurate is then that map that we got? Okay, good. And my name is Gerard Heuvelink, but you know that already. Okay, so what is this statistical validation? Because validation is used for many purposes. Well, in our terminology, the way we interpret validation is that we have this map that we made. Now we want to know how accurate is this map. Can we somehow quantify how close is the map to the truth, to the true, real soil property? And one obvious way to evaluate this is just to compare the map with the truth. So what we could do, for example, if we have independent validation data, I think it's all quite familiar to you, we could compute the mean error. So basically what we do is we have our study area, and what I've done here, I put it here as a sum. You might also want to use it, so it's really a sum symbol over here. Actually, because a study area has an infinite number of points, it should be a mathematical integral. But we could say, like, okay, we discretize our area so fine in such a high resolution grid that we actually have a finite number of locations in our study area, just to make it a bit easier on you, that we can still use the sum notation. But this capital N is all locations in our study area. And so that will be like a 1 million points or 1 billion points even, actually it should be an integral. So that is what we really want to know. We want to know how well do we do at each and every point in our study area. At each and every point, we compute the difference between the true value, Z. Yeah?
Can I just show one thing?
Am I doing something wrong?
No.
Yeah.
This one, because this is the screen is being recorded. So what I'll do, I'm just trying. This is a slideshow. Thank you.
We're okay. Yeah.
Sorry.
That's okay. No problem. So at each and every location of our study area, we compare the true value with the predicted value. We look at that difference and we take the average of that. That would give our mean error. Of course, we also would be very interested to know, because the mean error, the problem there is that the positive and the negative errors, they cancel out. So you're only looking at like a systematic difference. We also would like to know on average, the mean squared error. So that the positive and negative errors do not cancel out. And maybe we would take the square root of this to get the root mean square error. Everybody very familiar with that. What we also often want is to know the amount of variance explained. And some people call that the R square. And we had, with Mario, we had a discussion yesterday evening. So, you might also call that R square, but you have to be a bit careful there, because R square, like for example, when you do linear regression, is actually the square of the correlation coefficient. So it's really looking at whether the predicted and observed values satisfy a linear relationship. But you don't want to know whether they satisfy a linear relationship. You want to know how close are those points to the one-to-one line. How close is predicted to the observed. So I prefer to call that then the amount of variance explained. In hydrology, they call that the Nash-Sutcliffe coefficient. Maybe you're familiar with that too. And this is really about, well, that number actually also can be negative, because if your model is doing such a bad job that you actually do worse than just taking the mean of the observations, because as you can see here, we compare, basically we take the ratio here of the difference between true and predicted squared. That's summed over all locations in the study area divided by the true value minus the spatial mean. This is the spatial mean with a horizontal bar on top. So we're really comparing how well does our model perform to a model that just takes the average of all the observations. You might have models that actually do worse than the average, and then you would get a negative amount of variance explained. And with an R square, of course, you can never get a negative value. So it's good to be aware of that. Now, these three measures, they're all based on when we make maps of quantitative soil properties, things we express in numbers, like pH or clay content. Now, sometimes we also predict categorical variables like soil type. Well, then we might want to look at the purity. So basically, the purity is just the proportion of points in the study area that are classified correctly. So the I over here is an indicator function, a binary function that either is 0 or 1, depending on what's in between brackets. If that is true, so if the predicted soil class at a location Si is equal to the observed soil class, then this I would be 1. If it wouldn't be, then it would be 0. So basically, purity is a number between 0 and 1. It just tells me the proportion of points correctly classified. So we're all familiar with these measures of accuracy, but they're important measures. But what I wanted to point out is here, really, this is what we're looking for. This is the average of your whole study area. The capital N represents all points in the study area. And in practice, therefore, we cannot compute those error metrics, those measures, because we do not know the true soil property at each and every location in our study area. Because if we would, we wouldn't need to do soil mapping at all. All right, so we just have the soil property already everywhere. So why would we do soil mapping? So what we do in general is say, okay, let's just estimate those mean error, root mean square error, and so on, based on a sample, a subset of all locations in our study area. A subset of lowercase n points. And lowercase n is just our sample from the study area. This is a much smaller number of locations than the capital N, because the capital N is all locations in our study area. But that tells us actually we're only estimating what we really want to know, because it's based on that sample. What we're going to discuss now is two cases. We're going to start with number one, which is the case where we can actually have the luxury, let's say, that we have some budget to do this validation. We can go back to the field and we measure the true soil property, and we can use probability sampling. So we would maybe use like simple random sampling, stratified random sampling, all kinds of probability sampling techniques. But basically it means that every location in the study area has a positive probability of being selected, and we also know what that probability is. Most of the time we're going to discuss now the case of simple random sampling, meaning that every location has equal probability of being selected. And when we selected one point, then the next point is independent from where the previous point was selected. So that's when we can afford to take a probability sample of the locations in the study area. Sometimes, and maybe that's 95% of the cases, We do not have that luxury, and we have to work with the data that we have. Let's call that legacy data, or maybe it's data collected by ourselves, but not having in mind a validation, but maybe those data points were selected using Latin hypercube sampling or whatever, or just for kriging, a regular grid or something like that. And then it's good to be aware that this is not a probability sample, and that means that we can do, it's less powerful than when you have a probability sample, but I hope to make that clear in the rest, in the next few slides. Okay, so let's start with the probability sampling, because, well, I told you I'm a statistician, so this is more about statistics than about a computer science. So, well, when we have a probability sample, we can make use of a sampling theory from statistics. And I guess most of you have had that during your statistics courses in the past, so we're just going to briefly repeat that. It may be a long time ago, but in principle, what we do when we do sampling theory of statistics, we are interested in some kind of population, and that population, well, in our case, is the whole study area. We are interested in that population. And we take a sample from that population because we cannot afford to visit all elements of the population. Like when we do, when we want to know how many people are going to vote for the Liberal Democrats in the next election, we also take a sample. We don't ask each and everybody in the population, right? So that's what sampling theory is about. So we have some kind of population of objects. In our case, the study area, and the objects are all the locations. And those objects, those locations, they have properties like the clay content, the pH, but they also have like a property, the prediction error, the true clay minus the predicted clay, or the squared error, the clay as predicted minus the true clay squared. So each location is an object. We look at a feature, a characteristic of that object, and then we are interested actually in the mean. For the population mean, we call that mu, right, in statistics. And that those objects, that population also has a population variance, sigma square, quite familiar to us, I hope. So this is really taking the sum over every object, the value minus the mean squared, and taking the average of that. So these are the things we really want to know. In our case, like I already said, so the characteristic of the object is not the clay content or the pH or the carbon. It's really the error that we make with our soil mapping, like machine learning prediction. So the difference between the true value and the predicted value, or the squared difference. So you can now see that this mu for the prediction error is really the mean error. That's what we want to know. The mu for the squared prediction error is the mean squared error. So this is, we want to estimate this mu of the population. And we estimate that population mean by taking the sample mean. Because we only have this sample, maybe we have only 200 locations in our study area where we actually can observe xi. And we use the mean of that sample to estimate the population mean. And we want to know now, how good is that estimate? How close is the mean of the sample to the true population mean? That's really what I try to convey here. What we're interested in is for the whole study area, but we only use this sample. Now, it's good to be aware that before we actually go into the field and use this probability sampling to collect our sample of xi's, actually that sample mean, it becomes like a random variable. And we all know a random variable is a stochastic variable. It's not one fixed deterministic value. It has a probability distribution. Why is it a random variable? Why does it have a probability distribution? Well, because we don't know beforehand where will we go. We do a probability experiment, basically. We randomly generate the locations where we will collect the samples. So if we would repeat the probability experiment, we would go to different locations and we would get a different sample mean. So it's good to be aware that the sample mean, so basically the estimate of the mean error, the estimate of the mean square error is actually a random variable. It has a probability distribution. Now, what does sampling theory tell us? Well, first of all, that sample mean will be normally distributed, approximately, if the sample size is big enough. So if we can afford 50 observations or 100 or 200, or you can be pretty sure that that sample mean, that random variable, will have a normal distribution. And the mean, the expected value of that random variable, is equal to the population mean. So this really tells me that my estimate will be unbiased, right? I'm probably telling you things you all know very well, but anyway, good to repeat. Yeah. No systematic over or underestimation. We know it, we can prove it, if at least we take a probability sample, a random sample from our population, from our study area. And we also know what is the standard deviation of that estimate, of the estimation error. That will be sigma divided by the square root of n. Sigma, you remember, is the standard deviation of the population, so basically the spatial variation of our variable of interest. In our case, the variable of interest, like I said before, it's not the clay content, it's not the carbon content, it's really the error in our soil map, or the squared error. So that sigma characterizes how variable is that error spatially. The less variable it is, the smaller the standard deviation of my estimation error will be. And also the bigger my sample size, and all intuitively very clear, and we're all familiar with that, is that the bigger our sample, the smaller the estimation error. Yes?
Sorry, I just wanted to know, the sigma, is it spatial standard deviation or just the standard deviation?
It's the standard deviation of the population, and the population is, in our case, a study area. So you have a population of objects. Every object is a location in our study area, and what do we measure at that location? The error, the difference between the true soil property and the predicted soil property.
So is there such thing as a non-spatial standard deviation?
Yeah, I mean, you could have a population that is, let's say, all the people in a country, right? And that population, or let's say the height of people. So one person is taller than another person. So you have a variance of that population too. So, but in our case, the population is actually a study area, locations. So you might call that a spatial variance. If you would compute a semi-variogram, then the SIL of that semi-variogram will be pretty much equal to the sigma square. Yeah. So what we learn is that the larger the sample, the smaller the standard deviation of our estimation error. But there's the square root sign. It's the curse of the square root sign. Let's say to make the estimate twice as accurate, we need a 4 times as big sample. To make it 10 times more accurate, we need 100 times bigger sample. And that's a bit confusing. So it's the standard deviation of the estimation error, but in statistics we usually call that the standard error. Okay. So standard error is also a standard deviation, but then a standard deviation of an estimation error. Okay. So we know now, because the estimate is unbiased, we know that the sample mean minus the population mean, it's a random variable, but the mean of that is 0, so no systematic over or underestimation. The estimate is unbiased, and the standard error gets smaller and smaller if at least we make the sample size bigger. We can quantify that, and that's really nice. And we will see later when we do a validation based on a data set that is given to us, which is not a probability sample. We will not be able to demonstrate these kinds of things. We just don't know about that. Okay. So why do we so often use the normal distribution? Well, that's because of the central limit theorem from statistics. We'll not go too very deep into that now, but basically that tells us that when you start averaging things, whatever distribution they have, log normal, uniform, triangular, I don't care. If you average samples, realizations from whatever distribution, but you take the average of those, then that average will converge to the normal distribution. Maybe a nice way of illustrating that is the Galton's board. So let me show that to you. So basically, we drop a lot of balls, right, into some kind of funnel, and then they enter this grid of pins, and it's a 50-50% chance going left or right. So it's really a binary probability distribution, but we take average of many of them. And then we collect the balls in bins. Well, yeah, surprise, surprise. It's a normal distribution. Let me see, that's it. Yeah. So, yeah, maybe that's more convincing than a mathematical proof. You can actually buy this Galton's board, you can build it yourself also too. So I'm really thinking about using that also with my students back in Wageningen, because they, yeah. That is quite convincing. Okay. Sure, no problem at all. Yeah. So where are we here? This is another example. The height of people. So I think maybe this is maybe in the 1970s. They all have a bit of hippie kind of clothing, looks like it. But so you just classify, you put every student in a bin depending on how tall they are. And if your group is big enough, we are 40 people. We could do it in the coffee break, but yeah, it will move towards this normal distribution. So actually it's nice also from a statistical point of view, because it's easy to work with the normal distribution. Now, of course, we also know that like lead pollution, carbon concentration is usually more like a log normal distribution with outliers, with extreme values. So you get a log normal distribution if you multiply rather than add independent realizations. So it's not that everything will be normal always, but the sample that we were talking about, estimating the mean error, the root mean square error, well, that's really based on averages of summing. So we do know that those estimates will have a normal distribution. So once we know that it is unbiased, once we know the standard error, and once we know it has a normal distribution, or is close to a normal distribution, we can also compute confidence intervals. And Tom used that already this morning. He used plus or minus 1 sigma. So usually in statistics, we often use like plus or minus 2 sigma, or if you want to do it properly, 1.96. We could look it up in a table of the standard normal distribution. So we know that for the normal distribution, 95% of all cases, the value is plus or minus 1.96 times the sigma from the mean. And while this requires that we know the sigma, well, we were really trying to estimate the mu, the population mean, and now we need the population variance to be able to calculate that. Well, we don't know that one too, so we would probably replace the sigma with the S, the sample standard deviation, if you remember that from statistics courses, and then the 1.96 will be a bit bigger number, taken from the student T distribution. I hope you remember that somewhere back in your head, and not important to us, but so then the interval actually becomes a bit wider, because we're also uncertain about the sigma. So the theory is really quite thorough. All that I told you now is really assuming that the sample that we take from our study area is a simple random sample. So every point has equal probability of being selected, and they're mutually independent. Now, that is usually not a very clever way of doing things. For example, stratified random sampling is probably more interesting. For example, you might have an idea that this part of the study area, I think I do better than that part of the study area, so you could subdivide your area in strata and then take a simple random sample within each stratum. And you get more efficient estimators then. So your standard error will be smaller for a given sample size. Even systematic sampling, it may sound a bit strange, but systematic sampling is, in a way, it's also a random probability sample if at least the starting point of your grid is randomly chosen. Okay, so it can be extended, but it all is based on a probability sample. So if we have an independent validation data sets, of course it has to be independent too, right? We want to know how good is our soil map, how accurate is it? And then we confront the soil map with independent observations. So those observations, of course, should in no way be used to actually compute the map. They should also not be used to, for example, optimize the M3, the N3 or the M-try or all these kinds of meta parameters of our machine learning model. They really have to be independent, because otherwise you're like fooling yourself. You get too optimistic results. So it has to be independent, and ideally it's also derived using a probability sample, because then we can prove that our estimate is unbiased and we can actually quantify how close that estimate is to the true mean error, the true root mean square error of the whole study area. Okay. Now, if we do cross-validation, and that's one of the next topics, yeah, then we cannot do that. We can compute the mean error, we can compute the root mean square error, we can compute the amount of variance explained, we can compute the purity, but these are just estimates, and we don't know how accurate that estimate is. At least we cannot use sampling theory, and I have no clue how else you could do it. And you also don't know that the estimate is unbiased. So there's really very much power in using for validation a probability sample from your population, from your study area. So if you are in the luxury position that you can afford a part of your budget, maybe it's only 3% of your total budget, to take a probability sample for validation, I would highly recommend that. Tom?
But if you have like a simple random sample,
yeah,
for training, and if you do cross-validation with it, then
yeah,
every random subset of simple random sample is a simple random sample,
yeah,
and then it's satisfied.
Yeah, I like your question very much, because I've been thinking about that too. So suppose you do machine learning, and your calibration data are actually a probability sample. Let's say a simple random sample from your study area. And then you do a cross-validation. You might say, okay, every point that I put aside, we'll talk about cross-validation in a minute, but we're already familiar with that. Actually, it's a simple random sample from the population. But I'm not 100% sure of that. And I asked Dick Bruss. Everybody here knows Dick Bruss. Maybe not, I'm not sure. But he's really the sampling expert. And I really would like to work with him and figure out if that makes sense, yes or no. So, but I think there's a lot of truth in what you're suggesting, that if your training data are actually a probability sample, like a simple random sample, then you can still use cross-validation and you can use sampling theory from statistics. But it's something that needs to be worked out. Yeah, because he was a bit skeptic, but he could not explain to me why. So, okay. So this is really area of research.
Nothing to check. I mean, if you have a random subset of the people,
I think, yeah. So, yeah. Now, of course, for mapping, yeah.
Well, I was just going to, I know you said it, but would a Latin hypercube sample meet that criteria of a simple, not necessarily a
probability sampling? Yeah. So I think Latin, like conditional Latin hypercube sampling. So I think it is a probability sampling, so that every location in your study area has a probability bigger than 1 of being selected, right? And that you know those probabilities, and that you also know what is their interdependency. But so I said we can extend from simple random sampling to stratified random sampling, systematic sampling. Of course, the statistical inference will change if you use a different sampling strategy. So if you would collect your validation data, because the idea indeed of using the calibration data also for validation. So let's do a probability sample of the calibration data, because then we can do cross-validation and quantify standard errors and so on. Then you would like to use a way that you cover the feature space well, that you cover the space well. So why not use conditional Latin hypercube sampling? It would work if that is a probability sample, and I think it is, but the statistical inference that goes with that sampling design has to be worked out and can be really complicated. So we probably need Dick Bruce to help us. Okay, yeah. So, maybe the message is really, it has to be like a probability sample to be able to use the sampling theory from statistics. Yes?
So how this whole thing works in the non-parametric sphere?
Like, you mean like machine learning or?
Distribution led. Because all of these are building upon
normal. So the population, like the lead, the zinc concentration in the study area, then nobody expects that to be normally distributed. It can be any kind of population, any kind of spatial structure, any kind of distribution, spatial distribution. You don't care, okay? The only thing you require is that the sample mean, well, you don't require it. You know from the central limit theorem that the sample mean will have a normal distribution. It does, at least if your sample size is big enough. Okay, yeah, that's just mathematically proven. So we did the experiment with the Galton's board, right? So yeah, okay.
Just the mean, just the mean has to follow it.
No, like I said, the mean of okay, yeah. So we want the mean because we are interested in we compute the sample mean as an estimate of the population mean, but it's not the mean of the clay content or the mean of the carbon. It's the mean of the prediction error or the mean of the squared prediction error, right? Like I had here. Let's go back. Oh. Over here, so this is sampling theory. We want to estimate a population mean mu, or a mean of, attribute x, but that attribute x can be, and it will be in our case, the prediction error of our map, or the squared prediction error. Could be anything, but we are interested in the spatial mean of that, because that is how we defined the mean error and the mean squared error. This is really about, on average, how well do we do for the study area. Okay. So if we don't have a probability sample, because we have this legacy data, people gave us data, or it was using convenience sampling or purposive sampling, well, we got those data, but it was not really based on random number generator. So we can still compute all those measures, but we just cannot prove that they are unbiased estimates, and we cannot quantify their accuracy. Just very briefly, some kind of illustration. So this is, well, here you can see that also, well, Dick Bruce again. I don't know why I mention his name so often now, but anyway, he was one of the co-authors. And Bas Kempen, you might be familiar with him too. He was our PhD student. And well, they predicted, made a map of the soil organic matter content in the province of the Netherlands. So this is the Netherlands. I'm not sure if you recognize the shape of our country. Amsterdam is somewhere over here. Wageningen is somewhere over here. And the case study is in this province. The Netherlands has 12 provinces. So this is one of the provinces. And actually, this is this big province. And we're looking only at this study area. I think this is a digital elevation model of the study area. Well, there's no legend there, but you know that Netherlands is quite a flat country. Our highest point is in the very south of the country. That would be over here. It's 330 meters above sea level. This is also where the Meuse data set is from. Yeah. Anyway, so, and here's, I think, a soil type map. And so they predicted the soil organic matter stock of various depths, all not so important for us. For us, it's important, okay, that validation that was done using stratified random sampling, so we get to know the mean error, the mean square error, root mean square error, the R squared, and this is probably then the amount of variance explained, like I mentioned before. And what is so special about this is that we can actually quantify how accurate are those estimates because we use the probability sample. So between brackets is always the standard error. So that allows us, for example, to tell whether the mean error is systematically significantly different from zero. So for the topsoil, it would be, because the mean error is much bigger than the standard error. But for the other depths, it's probably not significantly different from zero. And so really the added value of using probability sampling is that we can quantify the accuracy of our estimates of the mean error and the root mean square error and so on.
How did they justify this R squared? I mean, it differs so much and it goes from 0.7.
Yeah, well, we would have to read the paper. So why? I don't know. So why? Well, I don't know. That of course depends on the covariates that have been used. I think this may have been like a regression Kriging kind of approach. Maybe there's a stronger correlation of the soil organic matter with covariates in the topsoil than deeper in the soil. But then, yeah, and then it gets better here. Maybe there's some peat soils there. I don't know. Or it's the overall. Yeah. So isn't that something that you usually see? That you do worse? That covariates have less power when you go deeper in the soil?
Well, the values are also lower.
Yeah, the values are lower, so the measurement error in the lab, which is really random noise, is relatively more important. I don't know. It's not a topic of this afternoon, right? Yeah. Probably need to look at the paper, and the problem, I'm pretty sure that they give an explanation why the R square is decreasing so much.
Don't they use the logistic regression?
I think they use regression Kriging, but yeah. The paper is from 2011, so there was machine learning then, but I'm not sure that they used it. And I think, you know, I think in Chile was the digital soil mapping workshop half a year ago, and there was a lot of this. I wasn't there, but a lot of discussion on, okay, machine learning, is it good or is it bad? What's the, you know, it's a black box, but Tom says it's not a black box. But anyway, it's very data driven. And then the geostatistics, the regression Kriging is more model based. We have an explicit model. So, you know, I think the debate is not over yet. Okay, so and if the goal of mapping is to get an as accurate map as possible, if that's the goal of modeling, yeah, and I'm surely not against machine learning. I mean, I'm very interested in it. But so that may be very convincing. If the R square is higher, yeah, why not? Huh? But if the goal of your modeling is also to understand, to get more understanding of the processes and get some grip on, I mean, that's what we also often use modeling for, then, you know, a model that has an explicit formulation like Kriging with external drift might be something you don't want to just put in the dustbin, get away from it immediately. Okay. Actually, I have a few slides that is also, and I'm not here to defend geostatistics, but that also are, you know, important reasons why there's still added value in using regression Kriging. Okay, but that's for later.
The mass and the other data set we got for smaller data set, it's
Yeah.
better
Yeah.
accuracy.
Yeah.
And I was like thinking, why is that? Well, there is some overfitting and over-smoothing effects of machine learning.
Yeah.
But it could be when it's close to linear relationships, you know. Then you add a complexity which is not needed.
You know, I guess, probably you know what you're saying is when you use these machine learning techniques, you know, that you have bigger data demands than when you use a more simple model like regression or regression kriging, right? So the data requirements are higher for these nonlinear techniques. Now, if you want to know more about this, I would definitely recommend buying or reading this book. And I'm not going to explain that, but there's also a lot of discussion, and many people don't understand the difference between model-based statistical inference and design-based statistical inference. I'll be talking in a minute about this spatial cross-validation, and they make the same mistake that, you know, when you take a simple random sample from a study area, by design, the observations are independent. But the independence is really in the way you select your observations. So you take a simple random sample. And it may be that two observations are really close in space to each other, but they're still independent in the design-based framework. So the sampling theory from statistics is valid, even though many people say, oh, wait a minute, they're so close, they are correlated because they're within the range of the semi-variogram. That's not right, because, you know, from a design-based perspective, where the stochasticity is really in how you select your sampling locations, they are still independent, even though they might turn up to be very close to one another in space. And there's some really good papers, but this book also explained this on this controversy, this difference between design-based statistical inference and model-based statistical inference. Okay, anyway. I'm not sure if Tom likes that I show this book, because it's not, what do you mean, open access or?
Well, I hope the next version they make.
Yeah, might be.
Open access, but
yeah.
To have the,
I mean, there's a new paper, Dick first.
he
made
the code,
Yeah, he shares the code also. Yeah.
GitHub,
Yeah.
But it's not an open access paper.
Yeah.
Okay.
So we discussed this validation using probability samples. Now we want to move to the cross-validation, and assuming that the data that we have are not a probability sample. So there's two versions of that, you might say. There's the leave one out cross-validation and the Kfold cross-validation. I just assume that everybody very familiar with that, so I'm not going to explain that. You can read this here. We can still compute the mean error, root mean square error, all these kind of things, and they are estimates of the true one, but we just cannot quantify how good, how accurate are those estimates, because we cannot use the sampling theory from statistics. And why would people want to use Kfold cross-validation rather than leave one out cross-validation? Because it's computationally less demanding, right? So if you have a really big data set, you would probably want to use that. So it cannot quantify those accuracy of the estimates. That's really, not a nice property. But another problem is that, sometimes you have a clustered observations. So if you would do leave one out cross-validation, then you remove only one point from the cluster. So all the other points in the cluster are still there. They're close to the point that you removed. So your prediction at that point is probably going to be pretty accurate, because you have many points in the neighborhood. And Tom gave an example this morning, and I don't know what, this was really referring to this leave profile out cross-validation. So if we have a 3D digital soil mapping exercise, and we have profiles where we measure the soil properties at multiple depths, you don't just want to remove one layer and use the others to help predict, because you have observations too close. So you do want to somehow make sure that you don't over-optimistically compute your validation statistics. But also when you have a clustered data and you do leave one out cross-validation or even Kfold, then you're also probably getting too over-optimistic results. So that's why Alexander Brenning came up with the spatial cross-validation technique. So, you know, the paper, you can just download it, but I also download, there's a few things I mentioned here, and I have them here on my computer, so I'm happy to share them with you, or maybe Tom can take care of that. There is also, for example, I will show later a book chapter that I wrote for the pedometrics book, and that book is quite expensive. So I'm happy, we are being videotaped, but I'm happy to share that chapter with you. And I don't know what, is it Springer? I'm not sure what they will do, but I think it should be okay. I mean, we're a small group. Anyway, so we'll make that available. You can cut this out, right? Yeah. Okay, so spatial cross-validation. What is that? Basically, the idea is that when you do your cross-validation, you make sure that the point that you put aside and where you make your prediction, that there are no observations nearby to make the prediction at that location. You just remove them, or you do your Kfold in such a way that you never have no observations nearby to predict at the put aside location. And what they use is like, okay, let's take the semi-variogram range, because that's where there's still spatial correlation as a measure for that. But that's I think where it goes wrong in a way, because this is confusing like the design-based and the model-based statistics. And another thing, of course, is that when we compute the mean error, we're interested in the spatial mean error or the spatial root mean square error. Well, there are locations in our study area that are close to measurement locations, and we do better there. And we want to know that, right? So we don't want only to see how well do we do at locations far away from observation locations. We want to know how well do we do on average. So there's something fishy about this, but it tries to like compensate for the over-optimistic result when you have clustered data. And that's good because cross-validation can get over-optimistic results. One way they do it is when you do the Kfold cross-validation, you make sure that your folds are spatial clusters. So here is an example where we have, well, I think these are like 4 folds, and you do, you know, so when you have, you put this fold aside, so basically you predict at these 5 locations using the data at the yellow. We don't see what? Oh, you don't see the mouse. Oh, that's strange. So then I'll just use my finger, okay? Thank you, Marcos. Yeah. So you have like 1, 2, 3, 4 folds, although it says 5, but and then this is one of the folds. So you put that fold aside. So you predict at these 5 locations using the yellow observations. So you don't have measurements nearby when you predict here, so you don't get over-optimistic. Thank you. You don't get the over-optimistic predictions here that are actually too good to be representative, whatever that may be, of the study area. But yeah, I think this is then maybe overdoing it. Now we get over-pessimistic cross-validation statistics, perhaps, because we're really doing extrapolation here, right? We are using these data to predict over here, so we're actually extrapolating. And, well, when we do mapping, we usually do not extrapolate. So I'm not 100%, you know, I have some questions about this today. But you, in the computer practical or in the demo that we do later on, we will have a look at how this works out. And indeed, it shows that, well, I'm not going to tell you now. We will see what happens to the cross-validation statistics, just the regular cross-validation, and this what they call spatial cross-validation.
Would it be possible to estimate the semi-variogram of the data and remove the spatial correlation?
So you have a correlation between the calibration and the validation point?
How to remove that?
But so
It is there.
If you calculate the range of spatial autocorrelation,
Yeah.
and then you always take for cross-validation points at the minimum distance.
Did you pay attention 2 minutes ago? It's exactly what I said, right? So this is the extreme version where you, yeah. No, I'm not sure. Well, so what? I think in this spatial cross-validation approach, the default is that you make sure that there are no observations in your calibration or your prediction data set that are within the semi-variogram range from your cross-validation prediction point. So you just don't use them. But then I said, you know, that is maybe overdoing it, because in practice, when we do predict and we make a map, we also predict at locations that are close to measurement locations. And we also want to take them into account.
I remember that some models they use more than one.
Yeah, Moran's I is just something like semi-variogram, right?
Yeah.
Yeah.
They make the standard error of the prediction bigger according to the Moran I.
So they have some kind of compensation. Yeah. I would like to see that, but I think it's very difficult to make that correct. And you know, I'm a strong believer in this probability-based sampling. I think this is really the way, because you want to know the spatial mean of your error, of your squared error, how to estimate that. But okay.
Let's say the training data was probability sample.
Yeah.
Then you wouldn't recommend doing that.
Oh no, I would strongly advise not to use this. Yeah.
And, I mean, it's okay to use it, but the interpretation is not that that's the true measure. It's just then it's like for extrapolation.
Yeah, but then you would get a over pessimistic, and you would get biased estimates of your validation statistics. You would underestimate systematically the mean error or the root mean square error. So it would not be correct.
So I think if the number of folders for the special one is the folders number of folders is very big, many folders. So the special one is close to the non-special.
Yeah. So if we would do 100-fold cross-validation, we would get very small folds. So maybe we would have these 2 points, and then we would be using these. Okay, that's true. But well, anyway, it's a way of trying to avoid that you have calibration data close to your cross-validation point, right? And so the effect, well, that's interesting what you say, very interesting, because so the root mean square error that you get when you use this spatial cross-validation probably very much depends on the K that you use in your Kfold. I don't like that, right? I mean, so with a 10-fold, you get a different answer than when you do 20-fold or 5-fold. So which one is the correct one? Okay, well, I also shouldn't be too critical about it, because if you do cross-validation in general with clustered data, you get over-optimistic results. So you want to somehow compensate for that. But this may overdo it, and ideally you would have a probability sample to do your validation. So if you want to know more about this, so maybe this could be also an interesting paper to look at. But this is really about, well, it does also review cross-validation and data splitting, but it also makes a case for using probability sampling. Okay, that was all I wanted to say about validation, cross-validation. And like I said, we will be testing some of the things in the computer practical later, or in the demo that we will do. The second topic, it's a bit shorter, and I should be shorter, but is about this spatial prediction error. Okay. So when we do validation, we get really, if we do it in a proper way, we get measures of how accurate is our map. in terms of mean error, root mean square error, amount of variance explained, and so on. But it only gives us a summary measure. How well do we do on average for our study area? We maybe would like to know for every location, how well do we do? How good is our map? So we like to have spatially explicit measures of the accuracy or the uncertainty. How close is our map to the predicted value, to the true value? Can we do that as well? Well, we can, but we will have to make assumptions. Okay, so this is no longer model-free, like design-based statistics would be. So we make assumptions, and very familiar, I think, to most of us is what we do when we do geostatistics, when we do the kriging. So, you know, well, this is the Netherlands again, and the Meuse data area is over here, and now we go to the Ge. In Dutch, we would say geul, so maybe we should say geul now or something like that, make it easier for you. And actually, Tom showed that this data set already before this morning. So this is also a valley in the south of the Netherlands where we look at the lead concentration, the pollution of the land by lead. And here are all our sampling locations. So these were like more like transects across the study area, about 100 points. And maybe you can see that there is like a river flowing here. So close to the river, we have higher pollution than uphill because the source of the pollution is because of the sediment of the river. Are there any Belgians in the room? Oh, so because the Belgians, we can blame them for that, okay? Here is Belgium, and the river, the stream comes from Belgium into Netherlands. And they used to have the open mining, I think well, not anymore, but okay, that's the source of the pollution. The lead concentration, also zinc and cadmium, they're actually quite high, so it's a real problem. So when we do this kriging, and I did just ordinary kriging, we get this map. And Tom showed it this morning as well, and he also showed the machine learning prediction. But this is only a map. It is not the reality. So that's the nice thing about geostatistics, that we can also quantify how well we do. We get the kriging standard deviation map. I think we're all quite familiar with that. So this tells us at each and every location, the predicted, let's go over here for example, well, the predicted lead is about 400, but the uncertainty that goes with that is about 115 or something like that. So we have every location, we have predicted plus or minus the uncertainty, well, the standard deviation, we can compute a confidence interval or prediction interval from that and so on. So that's nice. And of course, with machine learning, and that will be in the next slides too, we want to do the same thing. I mean, that makes us pedometricians, digital soil mappers, so unique. We don't want just a map. We also want to know how good is that map. Because many fields in environmental science, they don't do that. And they just make maps and that's it. But we always want to quantify the accuracy as well. So once we have that standard deviation, we can subtract plus or minus 2 times or 1.96 times, and we get the lower limit of a 95 prediction interval and the upper limit based again. Well, now I make a normal distribution assumption, and this is not sampling theory. So this is really an assumption we make, and we should test it. And maybe for lead concentration, it's not realistic. So maybe we should work with a log transformed lead and assume that that is normal, or all these kinds of things that you learn when you do geostatistics. But making this assumption, and another thing, of course, what we assume when we do this ordinary Krieg and make maps like this, that we assume stationarity, a priori a constant mean, a semi-variance that only depends on distance between locations, all these kinds of model assumptions. But given these assumptions, this is the result. And we quantify the uncertainty. And the uncertainty, as you can see, is quite high because the difference between this map and that map is quite big, right? We can even, in geostatistics, we can use this spatial stochastic simulation. and generate what we call possible realities, like throwing the dice, that any of these 6 could be the true one. It's just that I don't know which one it is, and I show you here 6, but I could show you also 1,000 of them. That's the whole idea. Here's another example of that. This is just synthetic data, so it's not the lead pollution. Where, well, in the center of every circle, I measured my soil property, so there's no uncertainty there. But in between, yeah, I'm interpolating, so I make interpolation errors, kriging errors, and that means that the reality is not certain there. And these is just in an animation mode, possible true values. And well, if we, for example, look over here, so it can be green, yellow, sometimes even red. So we're very uncertain over here. And maybe over here, I think we are less uncertain because we have more observations nearby. Something we always get. I forgot to mention that here. Also here we see those transects popping up because the kriging standard deviation really is just a reflection of the sampling design that we use. There's nothing wrong with that, by the way, at least in my opinion, but given the assumptions of our geostatistical model, right? So it's not that this is wrong, but we made assumptions, and the result of making those assumptions is this is the uncertainty. If you don't like this map because it doesn't reflect, it's only a reflection of the sampling design, then you have to go back to your assumptions and say which assumption I don't like. Because if you make those assumptions, then this is the result. You cannot say, I like this map, but I don't like this one. But this one was made with the same assumptions as this one. So, okay, enough about that.
But
yeah,
a high
Mario.
uncertainty not necessarily means that the prediction is bad, no? It's just, it's more uncertain, but it's not necessarily a bad prediction.
So like, for example, let's say over here, this prediction, right, has a pretty high kriging standard deviation, right? I'm not sure if you say if the kriging standard deviation is high.
Not necessarily the prediction is a bad prediction.
No, well, yeah. When you do the kriging, you make a prediction. Well, we actually know that this prediction, given the geostatistical model, the true value of the lead concentration of the soil has this distribution, in a way, if we assume normality. And then here we would have the predicted value, like, let's say, 400. And this, well, that's the kriging status, like 600. So basically you would say that the lead concentration over there has a normal distribution with a mean of 400 and a standard deviation of 600. Well, that already tells us that maybe the normal distribution assumption not so realistic. But now maybe we should use log normal or whatever, but that's not what you were asking. If your kriging standard deviation is high, oh, I'm at the wrong. This is the predicted value, 400, and this is the uncertainty, 150, let's say, right? So, but it might be that this predicted value of 400 is actually spot on. Right? It might be because it is a probability distribution, right? So it might be that the true value is this value over here, but the true value might also be over here or over here. I mean, the true value has like a probability distribution with a mean given by the kriging prediction and a standard deviation given by the kriging standard deviation. Right? But it's like when I throw the dice, I can throw 6 times a 6 in a row. It can happen, right? But maybe I'm very. So I mean, I also sometimes ask my students like, what is the expected value of a throw with a die? Maybe I can test you on that now too. So I throw a die. What is the expected value of the outcome of a throw with a die? Yeah, these are the possible 6 possible outcomes. Every outcome has probability of 1 over 6. But what's the expected value? What do you get on average if you would repeat this probability experiment many, many times? Sorry?
The average?
Which is?
Something like 3?
Well, yeah, actually it's 3.5. You add up all the possible 6 outcomes and you divide by the total. And it's easy to derive mathematically. The expected value is just a sum over all possible outcomes, the outcome multiplied with the probability of that. And the intuitive explanation is what do you get on average if you would repeat the probability experiment many, many times. Now here we do that probability experiment only once, right? So that's a bit strange. I mean, we have this geostatistical model that says, are you familiar? Well, Mario, you mentioned yesterday, is soil variation random? Very famous paper by Richard Webster, the founding father of pedometrics. So, of course, soil variation and soil is not random. It's deterministic. It's governed by mechanistic processes, but we don't know them very well. So in geostatistics, and I think in machine learning probably too, in statistics in general, we treat it as if it were the outcome of a stochastic process. And that's what we do here too. So we say that the lead concentration of the soil at every location in our study area has a probability distribution. The center, the mean, the expected value is given by this map, but the spread is given by this map. So sometimes, that was you, Mario, by accident, you might be really close to the true value. But if these numbers are bigger, in general, you are wider off, further off, right? Yeah. Okay, let's continue. Okay, so we looked at this. Now, let's go to machine learning. And, well, I'm more of a geostatistician, so machine learning, I mean, I'm familiar with it. And but I'm not really into the topic, and especially in terms of quantifying the spatial uncertainty or the uncertainty when you do machine learning. So as far as I know, I mean, maybe the machine learning is a bit lagging behind in the sense that with the kriging, we are already quite familiar with not only making predictions but also quantifying the uncertainties of our predictions. Then machine learning took off also in digital soil mapping. We make predictions of the soil properties, but now we really want, because we are pedometricians, we want to quantify the uncertainty, the accuracy of our predictions. So can we do that also with machine learning? So Tom already mentioned soil grids before, because I work for Wageningen University, but I also work for ISRIC, where Tom also used to work, and we have this soil grids product. So the first version of soil grids was a 1 kilometer resolution, using regression kriging, so geostatistics. So we not only gave predictions, but we also quantified the uncertainty of our predictions. Then we moved to machine learning. We also went from 1 kilometer to 250 meters, but we had to give in. We only quantified, we only said, these are the predictions. We no longer quantified the uncertainties. So in our next release, we want to quantify those uncertainties. And we are using this quantile regression forest for that. So we're going to talk about that very briefly. And maybe we already used it this morning, in a way. So, and actually Tom told me about it, so I'm really grateful for that. So it's one way of quantifying uncertainties when you use random forest. So I think this is an active area of research, many developments. And for me, hard to catch up, because also the machine learning literature, I think maybe Tom defined it this morning. What is machine learning? Of course, they need statistics, but there's also computer science there. And so if you have like the Journal of Machine Learning, the terminology is a bit different from what statisticians use. So I sometimes find it a hard time to understand what they're talking about. There's also this term called statistical learning. Is that the same as machine learning, but that's maybe more from a statistics background? So I'm also a bit uncertain myself about that. Anyway, there's a lot going on. And maybe this next generation machine learning, they routinely quantify the accuracy of your prediction. That's what we would like, right? So one technique is quantile regression forests, and the other one, I just learned about it last week, again from Tom, called the jackknife, infinitesimal jackknife. I know what is jackknife and what is bootstrap and so on, but how that really works with, well, we'll come to talk about that in a minute, and maybe some of you know more about it than me, and I would be really grateful if you would enlighten me. But it's good to be aware that whatever you do, we only predict, we get those, like what you might call the marginal, the one-dimensional distribution of the uncertainties. At each and every location, we get a probability distribution. But we don't really get, at least not as much, not with quantile regression forest. So, okay, so the error here and the error here, how are they correlated? Or the error here and the error there, or here and there. So you don't get the full joint spatial probability distribution of the error. It's only the marginal one-dimensional probability distribution at each and every location. Because you need to, of course, characterize spatial correlation if you also want to have the correlations in your errors. And, well, machine learning is data-driven. It doesn't really quantify, characterize, take into account the spatial correlation. So it's good to be aware that it's still a bit limited in that sense. Okay, and we will look at both techniques and look at the results in this demo that we will continue. So, quantile regression forest. The next slide has the paper that explains it all. So you can look at that later if you want to know it more in detail. So let me try to explain the way what I understood. So if you do random forests, and I think this morning Tom showed this when you have the regression and then it just cuts off and comes, because you know when you do random forest, in the end it's very complicated, but in the end every prediction is just a linear weighted combination of the observations, and the weights are never smaller than 0 and never bigger than 1. So you get an affine combination. So you can never extrapolate in your observation space. And of course, the way these weights are computed is really complex with all those trees and the covariates are in there. But in the end, every prediction is just a linear combination of the measurements. And that gives us our prediction. So that is random forest. Now with the quantile regression forest, they use exactly the same weights that have already been calibrated before, but they replace the observed value by a 0-1 binary value, depending on whether the observed value at that location is bigger or smaller than a certain threshold value. And you can do that for any threshold value that you're interested in. And in that way, you compute the cumulative probability. So it's normally like a probability density would be like this, but the cumulative one is only increasing from 0 to 1, right? So the integral of the probability density. So you, for every threshold or cut, you can compute, or at least an estimate of that cumulative distribution at every location where you make predictions. So you have the uncertainty, you have the probability distribution of the true soil property at that location. You get the probability distribution. So basically, that's what it does. So it gives you the quantiles, and you can go back, so you get the percentiles too. So it really gives you the, okay, it's maybe a bit more work because you have to do it for all those values of t that you're interested in. So it takes a bit more computing time, but actually the calibration, the computation of the alphas, you need to do only once. Well, and this I already mentioned, so you get the marginal, this is the marginal distribution. This is only at the prediction location as not. And that prediction location can be anywhere. Of course, you would do that at every grid cell, but you don't get the joint distribution. Yeah. Okay. Yeah, this is the paper. by Meinshausen, and it's already from 2006. Actually, it's a pretty short paper telling you, okay, what does it do? And then there's a long proof of the consistency, that it works. But that was also too difficult for me to fully understand, and maybe I had also limited time to do that. So things can get quite nasty from a mathematical, statistical point of view to really demonstrate how that this works. Okay. And then, well, this jackknife infinitesimal jackknife, that's the paper, and I know even less about this, but because Tom told me about it last week, but it is implemented, and we will do it, a demo of that, and it's just another way. You know, jackknife is very similar to leave one out cross-validation in a way, or bootstrapping, where you resample your population, and by looking at the differences between the results you get for different resampled sets from you, those discrepancies tell you how uncertain you are. So that is, but this paper was, yeah, for me also pretty hard. So actually, I sort of gave up, or I want to try really. But one thing I wondered about whether it actually gives us, because what does the title say? It says confidence intervals. And what we actually want are prediction intervals, and they're not the same. Okay, so I want to check that. And we'll look at the code later, because you also have like, but we'll look at it later. But we have some kind of correction factor somewhere in the code that you multiply. And I wonder where that comes from, Tom. So maybe this method only gives you confidence intervals and not prediction intervals. And I'll explain in a minute what is the difference. But usually confidence intervals are much more narrow than prediction intervals. So does this method actually give us what we want? So I really want to learn, and maybe some of you know it or have studied it, but you know, something, work in progress, you might say, something that I'm afraid I cannot really tell you now. So just to explain you the difference between a confidence interval and a prediction interval, using simple linear regression. Okay, so here every red dot is one of my students in a course. So in one of the courses, I ask every student to step forward and type in their height, how tall they are, and their shoe size. And then we do, just to demonstrate to them linear regression. So we have on the x-axis the height of a person in centimeters. Yeah, Ahmed, I'm a bit walking. And on the y-axis, we have their shoe size. So, you know, if tall people have bigger shoes than short people. So we can use height as a covariate to predict the shoe size. And we see definitely a pretty high positive correlation. But of course, the relationship is not perfect. Knowing somebody's height doesn't tell them exactly what shoe size they have. Maybe there's a difference between male and female. We could include more covariates, blah, 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 blah. But just simple linear regression. So we have the red dots. These are our data points. And then we fit the linear regression curve, right? But it's only a prediction because the true values, they differ. They deviate from the regression line. So we like to know how uncertain are we actually. Well, we can quantify that with a confidence interval. These are the green dashed lines over here, or prediction intervals. These are the purple dotted lines. So what is a confidence interval? Confidence interval is really about how certain do I know the position of the blue line, the estimate, the expected value, the average shoe size of people with a certain height. Whereas the prediction interval is really about one individual, one person with this height. What is the shoe size of that one individual? So I usually then ask myself. So I'm 1.82 meters. So what is the estimate of my shoe size? Let's see. Maybe 42, right? How uncertain is that estimate, or maybe I should say prediction, of my shoe size? Well, that's really the purple ones. So it's quite a wide prediction interval. One individual, me. How uncertain are we about all people that are 1 meter 80 tall or 1 meter 82 tall? On average, what is their shoe size? Well, that's the green line. And that's what we call a confidence interval. That confidence interval will actually get reduced to 0 if our sample data set is infinitely large. But the prediction interval will never reduce to 0 unless the covariate explains all of the variation in your dependent variable. So it's good to be aware of that difference, and I'm not sure whether this actually gives it says confidence intervals, but what we want are prediction intervals, so we need to check this. Okay. A few more slides. So now we talked about validation, we talked about prediction errors that are spatially explicit. We can quantify them if at least we make some assumptions. Now, when we quantify those prediction uncertainties, we maybe also want to validate those, right? We want to know how good are our estimates of the uncertainty. Can we do a validation of that? Well, we might, for example, use the standardized mean squared error, which is really summing over all locations in our study area, and of course in practice we will do that using a sample. The true value minus predicted value squared, so this is actually how well do we do, but we divide that by the model-based, like Kriging variance or using quantile regression for us, our anticipated squared prediction error, you might say. The variance of your prediction error. So what you would like is that the standardized mean squared error is equal to 1. Because you might say that this is the observed error, and this is the expected error in a way. And you want your expected error to be a realistic assessment of the true error. So on average, you would like those to be equal. Of course, every individual location, they may be different, but on average, it should be right. So you like to compute this standardized mean squared error, and you want to check whether that is sufficiently close to 1. I think it was in the figure that Tom showed, you know, that figure that was based up of 4 plots. One of them uses this. Well, Tom used the z-score. If you're in geostatistics, you're also familiar with z-score. Z-score is really, the square root of this, you might say. Yeah. And another one that I really like is called the accuracy plot. And I have a bigger example of that here. So what is that? Actually, this slide I will show also tomorrow at the conference, but I can give it to you right now already. So what we have a, on the x-axis, we compute the probability, the prediction interval width, right? So we can have a prediction interval of 0.50, 0.90, even 0.10, or we go from 0 to 1. So we make a prediction, but we know the uncertainty, at least we modeled the uncertainty, so we can derive a prediction interval, given a certain probability that the true value should be inside that interval. Okay, so basically this says like, we expect, if we take, for example, 0.75, we say 75 out of 100 times, the true value should be inside that prediction interval. And then we check how often does it actually happen using our validation data. And so if everything went well, if we quantified our uncertainty well, then we would expect that we are really close to the 1-to-1, the black line over here. And if we severely underestimated the uncertainty, then we get things like this. So you're below the curve. Because, for example, if you would even end up like over here, let's say over here, you say, I expect that 75 out of 100 times the true value is inside the prediction interval, but actually it only happened 50 times out of 100. No good. But also you don't like to end up here. You say, I expect that 25 out of 100 times you're inside, and 75 out of 100 you're outside, but actually you were 50 out of 100 times inside, so you were too pessimistic. Okay? So I like these kind of accuracy plots. Okay, this is the book chapter that I mentioned. So if you want to know more about uncertainty and also about uncertainty propagation, something I didn't talk about at all, but you know, when we make our soil maps, we don't make the soil maps only for the fun of it. We want them to be used by users, and we want to tell them how accurate, how uncertain our soil maps are, and they want to know that uncertainty is that acceptable for the purpose of my study. So if you have a crop growth modeler or an erosion modeler or a greenhouse gas emission modeler, they need soil maps. So if we tell them how uncertain our soil maps are, they can then analyze whether that uncertainty is acceptable, yes or no, for their intended use by using uncertainty propagation techniques. Okay, so I'm happy to share that chapter with you. Okay, for the practical, we'll go here, but we did that before. Now I happily to hand over to Tom again. and there's another book, just to finish, that I'd like you to, okay, maybe also this is not open access, and maybe it's expensive, I'm not sure, but I think it's free. Well, and it's really a great book. It says introduction, so it's really an introduction, but I think, you know, the techniques are so clear and well explained. So if you are a bit of a beginner, you might say, then this would be an excellent book to read. Okay, so hand over to Tom.
I have one question. So if you do a cross-validation and the points and non-probability sample,
yeah,
but you have a bias in estimating absolute error. The absolute error of the absolute accuracy. Sorry. The absolute value of accuracy.
So what is the accuracy? Is that the mean error or the root mean square error?
Yeah,
or?
root mean square error. So,
yeah.
So you have a bias is estimating that root mean square error, right? There's a bias.
Yeah. So for me, like mean error is a bias in your mapping algorithm.
Yes.
Root mean square error is not only the systematic error but also the random error. But anyway, the root mean square error is defined,
yes,
calculated for all locations in the study area.
I'm talking about root mean square error. You do cross validation, but you know the points are not probability sample.
Right.
Okay.
Yeah.
So you have some bias. That's it. Absolutely in the value. But do you have also bias if you just do a comparison? So you're not interested how much is the root mean square error,
yeah,
but you just want to know which of the three methods is the best.
Yeah. Also,
you
yeah. So if your goal is really to know how well do I do for the study area as a whole, but you don't have a probability sample. So you might have a sample that is only from one corner of your study area, right?
Yes.
And then you compare how two methods work. How well do they do? And you say, oh, method A does a better job than method B. How can you claim that that's also true for the whole study area?
Yes.
You don't know it.
Yes.
You really need this probability sampling.
Okay.
To be able to, yeah.
Okay.
Yeah, okay. Yeah, no other questions, by the way? Everything okay? Okay, I should give you the mic.
Yes. Okay. What I wanted to... So I will talk about I will go through the whole process, and then I will mention some of the things that you saw from the Gerard slides, and then we can talk about it, and then I will run it also. So as I was running before, I think it's good that I run in front of you, so and then we can look at the structures and data, and we can ad hoc try different things. So that was, I think, last thing we were doing this thing with the sorting things, and then we made these quantiles, right? So this is this quantile regression random forest, and in Ranger you only have to specify it. So when you do the Ranger, you have to say quantreg is true. You see this argument, and this. So that means if you set this argument, it will do a quantile regression random forest. So it's a bit more computational, but where it gets very computational when you do predictions. If you do on a larger data set, it can get really computational. So
and the function is calling the quantile regression function, or it's
embedded in Ranger.
It's embedded.
Yes, it's all in C++, so it's the best implementation. But yeah, it's still computational. And this is individual. Remember what Gerard said? There's an individual prediction, and now the quantile regression random forest will say, well, if we look at the 67%, 2/3 of predictions, 2/3 of probability, it's from 640 to 1,139. And so you see, it's still quite a wide range, right? From 640 to 1,100. So it's still for that individual point, it's still a wide range. Also, what's very nice about the quantile regression random forest is that for each pixel, you can actually calculate a cumulative distribution. You could rebuild a distribution, and it doesn't have to be normal. It's not going to, most likely, if you have some skewed variable, it's not going to be normal, right? So you can calculate for each predictions if you want. You can calculate the full distribution. That's what Gerard was also showing.
But the assumption that Menkhausen explains in the paper is that the mean of the full conditional response should be the same mean as the target variable, or it can be valid. Is that correct?
No. This is not. So what you see here, that's not the mean. That's the quantile. So median, actually. That's the median.
That this is the median.
Yes, it will be a bit different. It's a very good point. It's not the mean. It's the median. So if I do prediction using the quantile equal to 0.5, and if I just do random forest, I get different numbers.
I did that this morning, and I looked at the difference map.
Yes.
Quite interesting.
Yes. Is it a big difference?
Yeah, it's quite big, and sometimes it's positive, and sometimes it's negative.
Yes. If it's a skewed, right? If it's a skewed distribution, then the median is smaller than the mean.
Yeah, usually yes.
Yes.
But I'm surprised by this because it's asymmetric.
Yes.
Right. But you have very big gap between the
lower and upper.
Lower and the median,
yeah.
And a much smaller gap between the median and the upper.
Yes.
Left skewed.
Yeah, but you wouldn't expect that.
Yes.
Yeah.
Yes, but I will have to compare this for the whole pixels.
Sure.
And then
Yeah.
And this is the distribution normally what you get. So you have most of the cases it will be lower because of this
So what you have here is the prediction interval.
Yes.
Right?
Yes.
Upper minus.
Yes. This is as expected, because it's a log normal variable. And then you can estimate also the mean, kind of the mean error for all pixels. So this is do you see this? This is mean error, so mean range for all pixels. And then this thing should match the prediction error. Or what did I write here? No. This one is lower than this one. But yeah, the numbers, they should match. In this case, there's a difference, but these two numbers, they should kind of match. Right? Because these are the individual predictions.
But the prediction error is based on the cross-validation, right?
Yes.
Yeah. And the RFQ is the regression forest.
Yes, but for the whole area. So the difference is if you have the area goes beyond, so you're extrapolating, and then the prediction error will be bigger probably, and then it's not going to match the RMSE on cross validation, right? Then it should be higher. But in this case, what do we get? The smaller than the RMSE, but not a big difference. I mean, it's something like 25% difference. And then there's this jackknifing approach, and this one is initiated with this thing, keep in bag is true. And then when you do the predictions, then you have to say standard errors, SE.
What is the first argument?
The first argument is keep in bag is true. That means that will initiate the jackknifing. Well, it will keep it for the further calculation.
Can you clarify briefly the difference between jackknifing, bagging, and bootstrapping?
I was supposed to Gerard to do that.
Actually, I googled, and we could do that now. Jackknife.
Yes.
It looks to me very much similar to leave one out cross validation.
Yes. Yes. There are lots of fancy.
Bootstrap is very different. Bootstrap, you have a sample of, let's say, 500 points. So you create a sample again of 500 points from that sample, but with replacement. Replacement. So you sample again from that sample.
Yes.
The same sample size, but some objects are sampled once, or twice, or 3 times, or not at all. So it's resampling with replacement. That's bootstrap.
Yes. And then you say the predict standard error, so not contract, but standard error. And then what you see is it's a huge difference. So here you have only 33, and this is what Gerard says. Yeah, so it's very narrow. It's very narrow. So what I wanted to just plot it next to each other, so I scaled it for the plotting. I don't claim that this is the same thing.
No, because I think if you go up to, so I had, stop, where the mouse, so this is really where I wonder, what is the justification for that? There is no justification.
No,
but now you just did it because you want to look at the pattern.
Yes,
yeah.
Yes.
Yeah.
I just wanted to scale so I can plot next to each other. And it looks similar, I mean, largely, except, okay, here's more distinct differences from pixel to pixel is a bit smoother. So that was that. Then the same thing for the other data set, which is a bit more complex. Now you have more points, 450. And the R square gets a bit higher. And then here you have the predictions, and here you have the quantile regression range, which I set to be like a 1 standard deviation. And then very interestingly, you don't see like with the ordinary kriging or universal kriging, you don't get this like a constant pattern, but you can see that some places, I mean, it looks like there's some places repeatedly there's errors, high errors. And then this thing just plotted in QGIS. Then for binomial variable, it's very interesting. In Ranger, you can do it 2 ways. I don't know if you do that, but if you treat a binomial variable, you can treat it as a regression problem, but you can also treat it as a classification problem. And I didn't know, and I was thinking, okay, that's different. And then Marvin told me, no, it's you get the same, exactly the same. And there's a proof, you can test it with the data. You switch in Ranger, you say, I want to treat it as classification and then work as a probability space, or you work as a regression problem, and you get exactly the same results.
Is that logistic regression? Or?
No, it's range. I mean random forest. So you don't do logistic, but you get the same. Nevertheless, what's different is the so when you do the so this is the probability and this is the regression. So this when you treat it as a classification, and this is when you treat it as regression, you get exactly the same values, but for the jackknifing here, and this is the quantile regression, it's quite different. So if it's a binomial variable, and if you do quantile regression, then I don't know, you get this, like, you don't get the smoothness.
But But the quantile regression comes up with the quantiles.
Yes.
Of a continuous.
Yes.
Variable.
And then you have 0 and 1. Yeah, and you have 0 and 1. Yeah. Yeah. It's very interesting. Yeah, but it does make sense, because you see here, you see that's the border between two soil types, and you see where the border is the highest error. Everywhere transition zone is the highest error. And also there's some confusion, some classes going up and down. So here you have the highest error also. But anyway, so that's for the binomial. And then for factor variable, you can do also a jackknifing, and it will estimate. It turns it other way around, so you don't get the R square, but you get this prediction error. And then you can also map. You can make an error for each class. Have you ever done that? So for each class, you have per pixel, you have the prediction error.
You have 3 classes here.
Yes, 3 classes, and then you map for each class. So for this class, it will be somewhere here's the highest, and then for this class, it's also on the transition zones. Usually transition zones, yeah. And then there's the spatial cross-validation. So Gerard spoke about that too. So this is implemented in the MLR package. So how does it work? You specify their coordinates. So you specify we're going to do machine learning task. So first we create in MLR. It's really nicely structured, I have to say. You know, it's like you first specify what you want to do, then you specify the models you want to use, and you specify how you want to fine-tune it, and then you run the training. So I think it's really, really nicely structured. So I highly recommend looking at that. So in this case, we specify that the target variable is zinc, and that it's a spatial data set, so we have coordinates. And so once you do that, learner, we can run it in parallel, and then we run spatial cross-validation. We do 5-fold, 5 repetitions, so 25 times. And then we get an error, aggregate error of 73,000. So you need the square root of that. And then you can repeat the same thing. You do the same thing, but we call it non-spatial task. And then we repeat the same thing, and you see we get smaller. We get a smaller error. It's not a big difference, but something like 10%. Do you see this? So you get, if you do a non-spatial, so if you don't account for where the points are, it's always a good chance you will get a bit smaller error. So it's a bit more optimistic. And so now we had, I think it was very good discussion today. I'm very happy with Gerard opening that up because you see I think this workshop, we're doing lots of stuff which is on the edge. We're now on the edge of science because I actually don't know many things. How will they develop and what we'll be doing next, and I'm not sure, for example, for ensemble machine learning, I read some articles, but I still don't have a solution to do a prediction error from ensemble machine learning. I don't know how to do it properly. And also I want to do it computationally efficient. I don't want something that I need to run simulations or something. I want that I get a good enough estimate and it doesn't cost me too much computing time. And so that's really on the edge. So maybe I will run now some things from here.
What is the standard time for your predictions nowadays? The global prediction.
Yes. So yes, I can tell you that. So this is the last one we were doing. It's this. Just to give you an example, this is the soil water content at field capacity. The solid models, the R-square, the cross-validation with the block cross-validation was okay, was like 0.75. And this is about 250,000 rows and with 250 covariates. And so modeling takes, I first do a fine tuning of models on a subset. I usually use like a 5% subset. Then I do fine tuning and then I do final model. And then the prediction altogether, it's done within 16 hours.
16 hours.
Yes. 16 hours computing, yeah. But no, I don't get any, there's no uncertainty. The only I have is the standard deviation of the two models, or three models if I use. So I only put that, but that's not the prediction error. It's just, it does show also differences in places where the errors are high, probably you'll have a high prediction error, but it's not one-to-one. So we can compute that. But this was, it was nice to see, like when you do this machine learning and we just have points and, and we get soil hydrological variable, and because we computed all these DM derivatives and on different scales, and then in predictions you see it does pick up. It picks up, like for example these valleys and deltas. It picks it up as places of probably higher field capacity. So we were lucky to see this like patterns coming up.
After the tuning and for building the final model, is not useful to get rid of the not important covariates for simplifying the prediction?
No, not for random forest, no.
Just for saving time in the prediction. I know that it's not going to be.
Yes, it will save the prediction time. It will save, yes. But I already, now if you look at this, for example, so if you look at this soil water content, so I will show you that. So this is all documented, of course. So here's the soil water content, and you see this is the R code. And so we already here, we use the principal components, right? And this is the variable importance for components. So the component 242, it's mainly correlated with the FPAR. There's the new Copernicus FPAR product, which comes up in many modeling as important. So it was really high quality. And but you see, it's like the drop is quite smooth. I mean, if you go the first 50, it's quite smooth drop. I mean, I think like soils and a couple of variables like ecosystems and stuff, they are dependent on many factors. There's not like they're just one or two factors, so they're dependent on many factors. But yes, also depth comes as important, which is, you can see then in predictions. I mean, you see if I scroll through depth, you can see how the values change. So of course with as the soil gets deeper, it has less sand, probably more clay, and then it has a potential to hold more water. It's higher. So anyway, yeah, it's about 16 hours. Okay, so I'm not going to run this in front of you. Imagine I say, okay, now we're going to run this, and but it's about 16 hours. What I wanted to run is this spatial cross-validation. So I will just show you that with the MLR, because we'll also have to stop. So as I said, I make this task. So that task is when I print it, it says, okay, 155 observations, and you see has coordinates true. So it's a spatial learner. So that's one of the reasons why Patrick also contacted me when he saw my post that I'm doing automated mapping with ensemble machine learning, and he says, yeah, we are very interested in this. Let's work together. Then I have this parallel map library. This is to parallelize, except this doesn't work so well on Windows. So then I will, I think, turn this off. Just turn this off. I run it without parallelization. So then we just say this, and then we say this one, and now you see it's running. Yeah. So it runs 25 times, 5 by 5, 5-fold, 5 repetitions, and then it computes the mean error.
Have you found sensitivities to the number of folds to use?
You could test it. I mean, you see, I can keep on repeating, and you see the numbers go up and down a bit, but probably they are circling around some number. And then if you can try. I mean, I think with this spatial cross-validation, as far as I remember the papers they made, what was very interesting, for example, to if you plot it. So let's see if this works. Is this thing? No. How do I get this? Which one was it? Yeah, to show this thing. You have to go back. Okay. Okay. So what happens with the cross validation? Like if you, so this is, let's say average spacing. So every spacing between cross-validation points. Okay, so as you increase that, what will happen is that the RMSE is going to grow, and that's what Gerard said. Eventually, if you increase it too much, so you have this basically separated clusters. You like test extrapolation.
Is it between cross-validation points, or is it between?
Sorry.
Point and,
sorry. Yes, cross-validation and training points. And so then what happens if you increase it? The RMSE gets higher, but then you are more like this is like extrapolation problems. But then usually what's interesting that you see that how it stabilizes. I mean, probably somewhere here at some distance it stabilizes. So that's then interesting. Where do you see that? So this is what they call predictograms. All these plots, when you see what happens when you increase the number of folds, when you increase the number of, you could also subset samples. If you have like a big point data set, like 10,000 samples, then you can subset samples, and you can see what happens with the accuracy. And this is what they call predictograms. So you plot the performance of a method in comparison to some criteria, and it's the same thing with the cross validation. Okay. And then I can do the non-spatial. Non-spatial is exactly the same. I don't say that it's there's coordinates, basically. So when I look at this, now has coordinates is false. And then I can do again training, and now the value is a bit smaller. And so that matches, what everybody writes, and also what I sketched here is that if you increase the coordinates, and if you force MLR to separate the points, you will most likely get a higher error. This spatial cross-validation, I told you I burned myself with machine learning because I actually ran on the profile data, and I got over-optimistic result. And it was wrong, because once I took the whole profiles out, then it was 20% or 25% lower R square, so higher error. So it was something that I reported that in a paper. In the +1 paper, we reported that the accuracy is high, but actually was lower. And it's only Travis Naumann that I worked out later on a couple of other papers. He told me, I was looking, and we have to be very strict about this, and because you want to give a number to the people, which is the accuracy they will have if they will just randomly go, like using probability sample, and they will go and measure that. So that's the number that you want to provide. You want to get as close as possible to that. If you don't have the money to do probability sampling,
then the paper would not have been accepted.
The paper is like we don't like go and I don't think we were overselling our accuracy. We were more like excited about combining point data in the world and doing like 3D modeling and releasing data and updating it quickly. That was the excitement of paper. So, but sometimes, the paper is about accuracy, and then if you say in accuracy, like we have a significant more accuracy, but your validation of accuracy was not, realistic, then you should really write back, and you have to publish like a correction or something. The other thing I wanted to show you, also very useful. So on this GitHub with wait, was it? Yes. So on this GitHub with all the examples and things, the GeoMLA GitHub, you can see the code from this paper, and here there's a lot of code. So just to give you an example, how much code a paper like this PeerJ paper, this one. So just to give you idea, like to produce all these values and things, I went and programmed basically from scratch. So there's these functions. So that's, I think, very interesting for you to see, to do the functions for cross-validation. And this is just for numeric variables. Okay? So I had to like rethink everything and reprogram together with the Madeleine actually. And so you will see we do a cross-validation by doing the both random forest and for the GOR. So this is for GOR. Yes, this is the code to fit variogram with the covariates. So do universal Kriging in GOR, and then to make predictions at cross-validation points. So I had to make all that, from scratch because it wasn't existent.
So Tom, this model you mentioned, and one of people said you have this iteration.
Yes.
Right? Estimate the trend, then fit the semi-variogram, go back, and so. But this does it in one go, right?
Yes, but you can subset 10 times. You 10 times to fit variograms.
Yeah, but that's why 10 times?
Because you want to do tenfold, but you want,
but
but
it's not about what we were discussing this morning about when you do the regression kriging. You said, I always split, most people do, first trend and then kriging residuals.
yes.
And this is universal kriging, so it does both, but without need for iterations.
Oh, but the GR, yes. GR does it, yes.
There's a maximum likelihood.
Yes.
Remmel.
Yes, Remmel. But it still doesn't iterate the regression coefficients and varium. Yeah, I'm not sure about that, but
okay.
But yeah, anyway, so I just want to show you when I started doing this, there was actually lots of code, and now that I made that code, I mean, I would like to now, I want to make a cross-validation functions for ensemble machine learning also, and then put it in this package, LandMap, and so that you can go and say, okay, now I'm interested. I have 5 models, and I have the distances and the buffer distances, and now get me. And then you also want immediately to compare that with the geostatistics, so like universal kriging in GR, and you want to see what, like you want to have a reference, I think. I think when you do like a predictive soil mapping, you know, if somebody asks you what's your error, it's this error. But you get much better effect if you say, well, my error is like 30% or 50% less than some standard geostatistical method. And so I want to embed that in the LandMap project, that you always have like a kind of a baseline estimate. And sometimes it will be maybe worse than the GR. It might be worse. I got it a few times worse. But then you know if you're going the right direction.
I guess that if you can meet the assumptions of a statistical model, there is no reason why a machine learning will be better. Would you agree?
No, it doesn't. It depends from case to case. You can have machine learning always better. So.
I think like what Mario said. Suppose you generate synthetic data.
Yes.
From 100% completely defined geostatistical model.
Yes.
Like ordinary kriging.
Yes.
Then you can never outperform the kriging because it's optimal.
Yes. Okay. If you synthetic data, yes, you could prove it probably. Yeah. But maybe some really good machine learning, even with synthetic data, will find that pattern. You know, it will come very close. But obviously, if you know the parameters, and you know, machine learning will never predict the parameters as the same accuracy as your knowledge. You know, it's so. Is that what you meant by yes? But this is only with synthetic data. I mean, and with the real life data, you don't know you don't know.
Mario said if the assumptions are met,
right?
If the reality satisfies the model.
Okay. Okay, I think we need a coffee break, and then we will go for the. Yes, sorry.
So in geostatistics, we say there's a minimum data, 100, 110.
There's not a strict number, but normally nobody will tell you go and fit a varium with less than 50 points.
Usually it's 100, but that's okay. So what about the machine learning?
Yes, I fitted the machine learning with 50 points. You can, technically speaking, but do you have gains? I mean, would you produce some gains with that? I'm not sure. You know, it's.
Is there like a rule between the number of covariates and the size of your data set?
No, not for like random forest. No,
okay.
There's no rule. I mean, I have more covariates than points. No problem.
Not a problem.
Yeah.
Okay. But then this.
But then you need more
M3 or try or this parameter, are they adjusted to this dataset size?
You can fine tune them. But I assume, I mean, at one stage, like let's say if you have 3 times more covariates than points, and some stage, you know, it's like you're just computing for nothing.
When you have a small data set, will it use fewer covariates than when you have a big data set? Random forest?
It depends if it finds correlation. Only then. If it
the same, let's say, the same study area, the same covariance.
so for
just try. How does it work out when I have 500 points or 2,000 points? Do I get different models, more covariance included or not?
Yeah, the patterns will differ a bit, but they shouldn't go like differ a lot.
Okay.
So if you have, let's say, a data set where you have 10,000 points and you subset to 100 points and you compare 100 to 10,000 points. So the pattern shouldn't be too different. Then something's wrong.
I'm not so much interested in maybe we shouldn't talk about this too long, we need a break.
Yes.
But in the patterns, but more in the structure of the model, whether it uses more covariance or fewer.
So the variable importance should be also similar.
Okay.
It cannot be the same, but probably similar. And the R square should be smaller, but not too much smaller.
Okay.
So yeah, it's very interesting for machine learning. It's once you have all the covariates and if you, as long as you subset in also probability way, you subset randomly, then the structure shouldn't change so much.
So if you have few points and a lot of covariates, you need to increase significantly the number of trees, because otherwise you're going to get all the points and probably not all the variables selected.
Yes.
So that's why.
Yes. But I think still that if you are like pushing too much, you're computing for very little effect. And that's also with machine learning, with computations, you have to be very careful.
If you say what you're saying is true, why should we collect a lot of data?
There's no reason.
Huh? We don't need that many.
No, it's more important where the points are than how many points you have. It's more important. For spatial problems, though, I notice if you take the whole world and you have you have now so many variables, climatic variables, landscape, geology, so you have so many combinations that if you say, well, I want to represent with the point all combinations or multiple points, then you need a lot of points, right? But if you just say, like, I want to make an estimate of soil carbon of the world, you could get a decent map probably with 300-400 points. But the question is that the points have to be like Latin hypercube sample. They have to represent the ranges of feature space. They have to be symmetric, so you don't do any extrapolation, and you don't have any bias in feature space. And so, anyway, that's what I believe. But it's also nice to have a lot of points, so because you can see what are the effects of subsetting, and you can maybe find some local correlations because you remember with the random forest, for example, you can localize things. You locally will predict a bit better if you have more points. Okay, let's do a break and we continue in 20 minutes.